This time we're taking a look at binomial distributions. So these are related to the binomial theorem expansions and things like that we've been working on from Pascal's triangle. So we're going to do little combinations and then probabilities of success and failure. And that's the important part here, is that everything we're working here is that it's either going to be a successful thing or it's going to be unsuccessful. So you either get what you want or you don't. And one of the questions we're going to look at, it's either going to rain or it's not going to rain. You're going to win the game or you're not going to win the game. And so we're looking at only two outcomes. We're looking at the outcome of either success or failure, thus the binomial portion of that. Binomial, again, bi meaning two. So in general, the probability of X successes in N trials is, so there's our probability, N choose X, so the total number of trials, choose the number of successes, which ones of those trials are successes, times the probability of success to the power of the number of successes we have, times the probability of being unsuccessful, times the number of times we would be unsuccessful. And you'll see this a little more clear once we start doing some of the examples. And then the expected value is just the number of trials times the probability of a successful trial. So if we take a look at a card game where we're repeatedly cutting a card from a deck and then replacing it, we want to know the probability of an ace being cut once or even 3 times. And I should add how many trials we're doing, so we're going to do this in 10 tries. So what's the probability of an ace being cut once in 10 tries? Well, probability of one ace is equal to, and now if we use our formula here, N is the number of trials, so we have 10 trials. We want one ace. So one success in 10 trials. And then the probability of drawing an ace from the deck is a 1 in 13 chance. So times 1 in 13. And that's going to be to the power of the number of times it occurs, in this case 1. And then times that, multiply that by the chance of not drawing an ace. So all the other hands that we don't get an ace, and I missed a piece here, sorry. So choose the hands that we don't get an ace. There's 9 times we're not going to draw an ace, and there's 9 tries left to do that. So 9, choose 9 times 12 out of 13, the chance of not drawing an ace, to the power of 9. So we're going to multiply that together, and when we do, it works out to about 37.43%. So 37.43 is our value there. So again, taking a look at that, we want to draw one ace in 10 tries. So there's our choose one time for it to draw the ace, the probability of drawing an ace, and we're only doing it once. The other 9 trials, let's select when they happen. There's only one way. Once we've selected our ace, there's only one more spot left for those to go. And then 12 over 13, that's the probability of not getting the ace. In those trials, we don't want an ace. So chances of success, we want 1 success. We want 9 failures to the power of 9. And that will work out to our 37% chance of getting 1 ace. Now, if we bump that up and we want to draw our ace 3 times in those 10 draws, then probability of 3 aces, 10 draws, choose the 3 aces, the 3 successes, okay, you're drawing the aces are success, times 1 over 13, the probability of drawing an ace, to the power of 3, because we're drawing 3 aces. Multiply that by 7, choose 7, which is the 7 remaining spaces available. We want to fill those with our 7 failures. Notice this is just going to be 1 times 12 to or 12 over 13, which is the probability of our failure, and we want our failures to happen 7 times. So this is draw 3 aces. There's a 1 in 13 chance for each of those aces. Draw your 7 failures out of the remaining 7 spots. There's a 12 in 13 chance of failing, the power of 7. And then we multiply that all out, and we get a 0.0312. So there's about a 3% chance of actually drawing an ace from the deck in the 3 times in those 10 trials. So again, the number of combinations we want. Okay, so this is our successes, probability of success, and the number of times that a success occurs is these 2 numbers. This is the remaining failures, always going to be hooked up like that. So notice if we compare that to here, there is no end choose part there because this really doesn't need to be there. These don't really need to be there because they're just going to be 1, so you can in general ignore that, but just to illustrate the concept. And then there is our failure. Okay, so if we look at another situation here, we are looking at working with a binomial distribution here. So we have a family with 6 children, and we're considering the probability distribution for the number of girls in the family. So first, what's our discrete random variable? What's our capital X? What's that thing that is our random variable, discrete random variable? That is going to be the number of occurrences of girls. So our probability distribution here is looking at the number of times we find girls in a family, in a family of 6 in this case. So calculate the probability distribution. So we could have no girls. We could have 1 girl, 2 girl, 3 girl, 4 girl, 5 girls, and 6 girls. And then we need to calculate the probability of each of these occurrences. So in the family, in general, you would have a 50-50 chance of having a boy or a girl. And I didn't leave enough room to do the calculation, so I'm going to do it off to the side here for the probabilities. We have 6 kids. Choose 0 of them to be girls times the 50% chance of it being a girl. So there's our 50% chance of success, but there's none of them. And then our 50% chance of failure, and there is 6 of them. So that probability works out to 0.015625. And then we just continue down with the same kind of process. The probability of 1 girl, 6 choose 1, times 0.5, the probability of success. So, and we have that 1 time, and then we're going to have 5 failures. And again, it's a 50-50 chance here. So there's our failures. And then the probability of having 2 girls is 6 choose 2. Choose our 2 positions for the 2 girls to happen, and then 0.5, and then to the power of 2, and 0.5 to the power of 4. 2 successes, 4 failures. 6 choose 3, 0.5 to the 3, 0.5 to the 2. To the 3 as well. 6 choose 4, and then we have 0.5 to the 4, 0.5 to the 2. So choose our 4 girls. 4 successes, 2 failures. 6 choose 5. So 0.5 to the 5, 0.5 to the 1. Successes, failures. And then 6 choose 6. 0.5 to the 6, 0.5 to the 0. 6 successes, 0 failures. And these numbers work out, and we get 0.09375, 0.2 0.234375, 0.3125, 0.23475, or sorry, 375. There, my apologies. And then 0.09375, 0.015625. So those are all the probabilities. Those are the calculations for said probabilities using our binomial distribution context here. And then if we multiply these together, x times px, we're going to get 0. We're going to get 0.09375, 0.4685, 0.9375, 0.9375, 0.46875, and 0.09375. In this case, this is all the possible cases that could happen. So the sum of the probabilities should be 1. So that's a way to verify, right? This is every possible case. We have either going to have 0, 1, 2, 3, 4, 5, or 6 children. So all their probabilities should equal 1 in this case. Now, if we want to graph this, we have about, I'm going to start in the middle here. We have about a 3.1%, or sorry, 31% chance of having 3 kids. So above the 3 here, it's going to go up to just above here. That might even be a little too high. Somewhere about here, just for a sketch of our graph. There's our 3 column. And then our 2 and 4, they're going to work out to about 23%. So let's say somewhere around here actually would probably work out well. And again, I'm just sketching this graph out. We can use technology, graph this using something like Excel or a graphing calculator program. And then our 5 and 1, that's going to be about 0.9, so just below the 1 there, so maybe about right here. So here, and should be about the same over here. It should be the same over here, so about right there. And then having no girls is going to be 1.5%, so we're somewhere down here. And then somewhere down here, give or take. So there's my approximate probability chart. Notice it has what we call, this shape here is a bell shape, or a bell curve. So you might hear of a grading concept, of bell curve. That's not one we use, but it is one where most of your students should be around this area here in the middle. So your proportions of expectations should be somewhere around the middle for most people, and then a few people on either fringe end. If we continue on with that, the last part there is we want to calculate the expected value. So when we're calculating the expected value, we're taking and why won't you focus? There we go. Focus back in. We're taking these and we're summing all of these values here, x times the probability of x. If we tally those all up, we get 3. So it's EX, and it's capital X because, again, it's the expected value of the whole situation, not the lowercase x, where here it's lowercase x because it's each individual case in that probability. This is the entire situation, the number of occurrences of girls. The expected value that you would get is the 0 plus 0.9375 plus 0.46875 plus 0.937. Oh, sorry, did I do that? 0. 0.9375 here. 0.9375. This one is 9375 plus 0.9375 plus, continuing down here, 0.46875 and finally 0.09375. All that should tally up to 3. And so on average, if you have a family of 6 kids, you should expect to have 3 of them being girls. So now moving on, we can also take a look at situations where we apply our distribution. So we know that one month, 8 days in that month had a 40% chance of rain. And so what we want to do here is figure out the probability that it rained on fewer than 6 of those days. So we have the case of it raining on 5 days, on 4 days, on 3 days, on 2 days, on 1 day, or on 0 days. So that's 6 different cases we got to look at. Or we can look at it in terms of 1 minus the failures. So what's the chance that 1 minus the chance that it rained on 6 days, 7 days, and 8 days, which would only be 3 cases. So we're going to do the indirect method here. Both ways work. The indirect method is just a little shorter. So the probability that it was less than 6 days is equal to 1 minus the raining on 6 days minus raining on 7 days minus raining on that it rained on 8 of the 8 days. So this way here, again, we're just doing the indirect method because this gives us 3 of these calculations that we have to do versus having to do a whole 6 of them. So less chance of error. So 1 minus the chance that it rained 6 of the 8 days is 8. Choose 6. Pick those 6 days. The probability that it rained is 0.4. And so to the power of 6 times 0.6, the chance that it didn't rain to the power of 2. Those 2 days that it didn't rain. Minus 8, choose 7. Times 0.4, the chance that it rains on 7 days, to the chance that it doesn't rain on 1 day. And finally, 8, choose 8, and the chance that it rains on all 8 days, and then the chance that it doesn't rain on none of the days. So to the power of 0, and that is a 0 tucked in there as I'm running out of space. When we calculate that all out, step by step by step, we end up with a grand total of 0.95 or 95% chance. And that is 1 minus raining on 6 days, raining on 7 days, raining on 8 days. Again, you should get the same answer if you did this. It would have been 8 choose 0, 8 choose 1, 8 choose 2, 8 choose 3, 8 choose 4, 8 choose 5, and 8 choose 6. It just would have been a few more to do, and I didn't give myself very much room to work on it. So that works out there as 0.95 or 95%. And then what is the expected number of rainy days? And so if we take a look at our expected value formula, that is the number of occurrences we want times the probability. So our expected value is equal to our 8 days times the probability, 0.4. 8 times 0.4 is going to give us a 3.2. So we would expect it to rain 3.2 days. And again, that's not a whole number. That again is just what we looked at as our expected values. Expected values do not have to be whole numbers.